Hey everyone, and welcome to today's Explainer. Today we're going to be looking at something that is absolutely foundational to literally everything we do online, DNS, or the global hierarchy of internet address translation. Now, I know a lot of people tend to think of DNS as just, the boring networking plumbing of the internet. But today, I really want to change that perspective. I want us to explore DNS not just as a bunch of hidden pipes and cables, but as a massive, living, breathing digital universe powered by these incredible, glowing information pathways. It's a constantly moving, highly coordinated system that flashes across the globe in a matter of milliseconds. Okay, let's dive right into this.
To really wrap our heads around what's happening here, we need to start with one central question. How exactly does a human-readable name actually become a digital destination? I want you to imagine just for a second that you're going to visit a friend who lives in a completely different city. You probably don't sit down and memorize their exact geographic coordinates, right? Like, you're not pulling up their latitude and longitude. No way. Instead, you just know their name. You reach out to them, you get their specific street address, and then you travel there. Well, the internet works in a very, very similar way. Every single website you visit lives on a server somewhere in the world, and that server has a unique, exact mathematical coordinate. But let's be real. As humans, we just don't think in mathematical coordinates. And that brilliantly illustrates the massive divide we have to cross literally every single time we open up a web browser. On one side, we have human memory. On the other side, machine language. We love friendly, easy-to-remember names. We love just typing in google.com or netflix.com. But computers? They absolutely require numerical IP addresses to communicate, things like 142.250.183.78. If we didn't have a reliable system to constantly translate between these two languages, you'd have to memorize dozens of ridiculously long strings of numbers just to, check your email or watch a quick video. That would make the internet incredibly frustrating and practically unusable. So to bridge this massive gap, DNS was created. You can really just think of it as the internet's ultimate high-speed phone book. It instantly translates our human-friendly domain names into the machine-readable IP addresses that computers need, and it does the whole shebang in milliseconds.
So how exactly does this global phone book actually work? Let's move right into Section 1, the epic lookup journey.
The exact millisecond you type www.example.com into your address bar and hit enter, the journey actually kicks off right inside your very own computer, because naturally the system wants to be as fast and efficient as possible. So step 1, your browser checks its own internal cache, basically its temporary storage vault. It's asking, hey, have we visited this site recently? Do I already know the IP address for this? If that vault is empty, we move right along to step 2. Your operating system checks its own cache. If it still draws a total blank, well, that's when we have to hand the quest over to the outside world, specifically to something called the DNS resolver. This DNS resolver is usually provided by your internet service provider or maybe a massive service like Google DNS or Cloudflare. It takes over the mission, stepping out into the wider internet on your behalf to hunt down the specific IP address. Now, if your resolver doesn't already have the answer saved, it begins what I kind of like to think of as a cinematic relay race through the global DNS hierarchy. First up, the resolver visits the colossal root server nexus. There are root servers distributed all over the entire planet. The resolver essentially asks them, hey, where do I find information about .com domains? The root server doesn't have the final IP address, but it points the way to the top-level gateways. So step 2, the resolver moves to the top-level domain, or TLD server, like the main servers for .com or .in. The resolver asks, okay, where is example.com? The TLD server then points it to the final boss of our journey, step 3, the authoritative DNS server. The resolver asks one last time, what is the exact IP address for example.com? And the authoritative server finally hands over those precise numerical coordinates. Boom, journey complete.
But what exactly is that authoritative server actually handing over to us? Well, that brings us to Section 2, decoding essential DNS records.
You see, when the resolver finally reaches that authoritative server, it's hunting for specific DNS records. You can think of these as living digital keys that tell the rest of the internet exactly how a specific domain should behave. Let's break down the most critical ones you're going to encounter. First up, the A record. Just think of this as a glowing address beacon. It maps a domain directly to an IPv4 address. The AAA record does the exact same thing, but for the newer, longer IPv6 addresses, which is super important as the internet keeps growing. Then we have the CNAME record. I actually love visualizing this one as a shape-shifting pathway. It creates an alias, pointing one domain name over to another domain name, rather than pointing to an IP address directly. Next up is the MX record. Picture these as highly efficient encrypted mail drones. They handle all your email routing, telling systems exactly where messages for a certain domain should actually be delivered. Then there's the TXT record, which stores text-based information. These usually act kind of like digital ID badges for security and domain verification. And finally, the NS record. This specifies which authoritative name servers are actually responsible for the domain in the very first place. All of these individual records are working together behind the scenes to strictly dictate the flow of all global traffic.
So, with billions of people clicking links every single second of the day, how does the internet not just completely collapse under the weight of it all? Let's check out Section 3, Speed, Caching, and Security. To prevent global server overload and defend our devices against massive data storms, we rely on a few absolutely crucial mechanics. The ultimate efficiency hack in the entire DNS universe is caching. And caching is governed by something called TTL, or time to live. TTL is just a value that controls exactly how long a DNS response is temporarily stored in a cache before a brand new lookup is actually required. I mean, imagine if every single person who visited Netflix right now forced a brand new lookup journey all the way up to those root servers. The system would literally melt down instantly. Instead, when your resolver gets the IP address, it looks at the TTL, which might be an hour, maybe a day, and it just saves it. Caching reduces latency, it minimizes network traffic, and it drastically speeds up web page loading times for billions of daily requests. It really is the silent hero of internet performance. But here's the catch. With all this highly sensitive information being handed off and stored globally, security becomes a really massive concern. Like, what if a bad actor injects fake IP addresses into those local caches? You might type your actual bank's URL, but get secretly sent straight to a hacker's server. To stop this from happening, we use DNSSEC, or Domain Name System Security Extensions. This security protocol adds cryptographic signatures directly to DNS data. If you're looking at this from a cybersecurity perspective, you can literally think of DNSSEC as wrapping the DNS records in these invisible golden energy shields. It mathematically verifies that the data genuinely came from the true authoritative source and absolutely wasn't tampered with along the way. It protects everyday users from severe real-world threats like DNS spoofing and cache poisoning, ensuring you actually end up exactly where you intended to go.
All right, now that we've covered the mechanics, the records, and the security side of things, let's tie all these concepts together. Section 4, Powering Global Cloud Infrastructure.
For anyone out there looking to truly understand how massive digital services operate across the globe, this is where the theory becomes reality. Let's walk through a real-world example at hyperspeed. Let's say at 0 milliseconds, a user in India types www.netflix.com and hits enter. By 10 milliseconds, the local browser and OS caches are checked. They're empty, so the resolver immediately steps in. By 50 milliseconds, queries are flying all the way across the globe, checking the root server, hitting the .com TLD server, and finally finding Netflix's authoritative servers. And at exactly 100 milliseconds, literally just 1/10 of a second, the exact IP address is returned. The resolver caches it using that TTL value we talked about, and the browser securely begins loading the movie. I really just want to emphasize this to you. This entire massive cinematic coordination flashes across the world in literal fractions of a second, completely invisibly to the person sitting at the keyboard. It's wild.
The really crucial takeaway here is that whenever you create APIs, email services, or any kind of global infrastructure, DNS is going to be involved. If you're an aspiring cloud engineer or developer, mastering this is absolutely essential. Let's look at another real-world scenario. Configuring a custom domain for a brand new app. You wouldn't just point your domain to one single fragile server, right? No, you'd configure your custom domain's A record to point to a global load balancer's IP address. That load balancer then totally relies on DNS to intelligently distribute all that incoming traffic across massive global server clusters. If a server in Europe suddenly goes down, no problem. Engineers use DNS records to instantly update and point all that traffic over to a healthy cluster in Asia. Setting up high availability, ensuring seamless global scalability, connecting your custom domains, literally every single bit of it is built squarely on top of the DNS foundation.
So, as we wrap up today's explainer, I want to leave you with a final thought to chew on. DNS quietly powers the internet every single second of every single day, and it forms a critical foundation for every future software engineer. Let's just zoom back out to that macro view of Earth's glowing information pathways. Every single website visit, every app connection, every background API request relies on this incredible system working perfectly day in and day out. The next time you type a simple, friendly name into your browser, I really hope you remember the incredible global relay race that happens in the blink of an eye just to connect you to the rest of the world. Because at the end of the day, if you control the DNS, you control the traffic of the entire internet. So what kind of digital pathways are you going to build? Keep exploring, keep learning, and I'll catch you guys in the next
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future BreaK CodeR, because many exciting coding and futuristic tech videos